All right. Hi there, everybody. For those of you watching the recording, I wanted to start off by answering a couple of problems about the web work that I got questions on via email. So in 6.1.1, there's a question about that one. So we want to find the number of elements in the union of these three sets. If there's 100 elements in A1, 1,005 in A2, and 9925 in A3, if the sets are pairwise disjoint. So why don't you guys help out here? So what does that mean? The sets are pairwise disjoint. Yeah, there's no common elements, right? So if there's no common elements between any of the sets, we add them all up. That's exactly right. So we would have, let's see, 9925 plus 1,005. That'll be, yeah, that's the final answer. Okay, I believe you. 11145. Okay, cool. And what if A1 is contained in A2, which is contained in A3? Yeah, then A3 is the number of elements because the other two sets are inside of it, right? So they're all common elements instead of no common elements, right? So this would be 9925, right? In this one, there's 17 elements common to each pair and 5 in all three sets. So what's going to happen with that?
Hey, sorry, I just realized that the number I gave you for A is probably wrong because I have different numbers in my problem and was just
Oh,
going off the
gotcha.
top of my head there. Sorry.
Here, let me, no, that's fine. Let me use Google. So we got 100 plus 1,005 plus 9925. Okay, yeah, it's different. 11,030 is what it should be. Okay, 30. Okay, cool. And then lastly, there's 17 common to each pair and 5 in all three, right? So in that case, right, what are we going to do? Like, how's that going to work? The 5 is included in the 17. That's right. Because if there's 17 common to each pair, and then 5 in all three, then those 5 would also be common to each pair, right? So maybe we should draw a little diagram here. Let me do that. Okay. So here's what we've got. We've got these sets, A, B, and C. Okay. We know that common to all three of them, there's 5 in there. So I should have made that bigger. Sorry. There's a 5. There we go. There's a 5. Okay. And then if there is 17 common to each pair, how many is going to be in this region here? Yeah, 12, right? 12 here. And same for the other ones. There'll be 12 here and 12 here, right? Now let's take the first set, A1, which had 100 total elements. Well, if there's 100 total elements, 12 here, and 5 here, then how many are going to be left in the sort of the big region? Yeah, 71, right? Because it'll be 100 minus 12 minus 12 minus 5. So we're going to subtract off 29, right? And 100 minus 29 is 71. Okay, then we have 1,005 over here. That's going to be minus 21. So that'll leave us with 1,004 minus 20 is 984. Right? And then lastly, we have 9925 minus 29. That's going to give us 98. Let's see. minus 4. So that'd be 96, right? And then you'd want to add up all these numbers. Yeah? Is everybody happy with that analysis? Any questions there? Oh, did I do the subtraction wrong? Uh-oh. 976. Okay, minus, yes, thank you. 976. Yep, that was wrong. Cool. Okay. Then let's talk about the other question I got on email, which is 6.6 or 616. All right. So again, it's one of these sort of 3-set problems, right? 330 people are the total number of people surveyed. 120 like Italian, 210 like Mexican, 220 like American. If 60 like both Italian and Mexican, 75 like Italian and American, and 100 like Mexican and American, how many people like all three, right? So essentially what you've got here is sort of another setup where you're trying to find, the numbers that fall into which region of those three overlapping circles in the Venn diagram. That just the order is going to be a little bit different on this one, right? So let me pop back over to my video here. Okay, so for this one, we're going to have another setup of a Venn diagram. Okay, and for this guy, we have 330 people total, right? But now we know that in the intersections, let's do Italian, Mexican, and American, right? So we know that in the Mexican category, we have 210 total. In the Italian region, we have 120 total. And in the American, we have 220 total. Okay. We also know that 60 like both Italian and Mexican, right? So Italian and Mexican, there's 60 in here, including the center region, right? That's included. 75 like Italian and American, so 75 goes in here. And then 100 like Mexican and American, so 100 goes in there. So then the question is, well, how many are going to be going in this center spot, right? So how could we figure that out? If we know there's 120 in the whole region, right? And we know that there's a 60 and a 75 and then some mystery amount, right? How can I figure that out? Okay, so you've got a formula there, David. You have m plus I plus A equals 330 minus all the overlaps minus overlaps. That's the two sort of the two set overlaps, then plus the center. Okay, so why is that? Okay, because you count the overlaps twice and the center 3 times, adding in all of them. Okay, so if we add everything up, you know, we get 330, right, for the total number of people. But here what we're doing is we're saying, okay, we're going to take all of the people that like Mexican food and all of the people that like Italian and all of the people that like American, and we're going to count the overlaps twice, and we're going to count the center 3 times, right? So if I subtract off the overlaps, right? So in other words, if I do M plus I plus A, what's that going to be? Well, that's going to be my total 330 plus 3 overlaps, right? Which include the center. Maybe let's not include the center, right? We have the 3 overlaps, the non-central overlaps, these guys, right? So we'll have 330 plus an additional one of each of those, plus how many times is the center repeated, plus the center was repeated 2 extra times, right? So we'll say, okay, well then in that case, if we want to find out the center, right, then we would, so we would want to subtract off those overlaps. Maybe we should subtract off a center as well. So I'm worried, you know, if we subtract off the overlaps and add in a center, should we be adding the center times 2? So David, okay, so you wrote it backwards. Well, so you do know what's in the overlaps, you don't know what's in the center, right? Okay, so I was right in my argument. So maybe we should write the equation a little bit differently. So let's write it as 330 equals M plus I plus A minus the 3 overlaps. Okay, let's include the center this time. So 330 is all of the I plus all of the M plus all of the A. Then we're going to subtract off this overlap, 75 plus the center, and this one, 50 plus the center, and this one, 100 plus the center, which means I started off, you know, I want to get each region included once is the idea, right? So I want this big guy in there once, I want this overlap once, I want this big guy once, I want the center once, right? So you want each region counted one time in order to add it up to make the total. Now, since we're double counting these overlapped parts, we should subtract off one of them, right? Minus one of each of the 3 overlaps. But when I do that, I'm subtracting off the center 3 times, right? I started with the center being counted 3 times because I counted it once for the entire I circle, once for the entire M circle, and another time for the entire A circle. So that center was counted 3 times here, M plus I plus A, and then subtracted 3 times here because it's included in each of the overlaps, which means the center has not yet been counted, right? So in order to include that, I have to add in the center, right? Which is exactly what you had down here, so plus center. So if you wanted to find how much is in the center, well, let's just do a little bit of algebra, right? Center, okay, would be 330 minus M minus I minus A plus the 3 overlaps. Right? Just switch the signs as we move this whole thing to the other side of the equation. Right? What do you guys think? Does that help? Does that make a bit more sense? Any further questions there? Alrighty, sounds good. All right. Does anyone else have any other questions on the web work or on the proofs or anything else that I can answer for you? You have a question on which one? I'm sorry, go right ahead.
On this last one really quick, Nick. So
Yeah.
if you go through and solve that, I got this one right. I did it a slightly different way with kind of, you know, just, but very similar. Does this, and I was confused, like it seemed that, would this give a kind of like an at least amount, like the minimum amount of the center? Because I found it kind of hard to prove that that was for sure the amount in the center and not just a kind of the lowest possible amount of.
Gotcha. No, it's exact. So it's not like a lower bound or an upper bound. It's exactly the right amount. And the reason why is because you're adding and subtracting these sections like a fixed number of times. And so once you account for all of those additions and subtractions, you will get an exact amount. Does that make sense?
Yeah, totally. Thanks.
Okay. Yeah, sure. Okay. Other questions on this, on other web works, on proofs? What else can I help with? Okay, sounds good. Well, in that case, let's jump back into the material from the book. And last time we had left off on our with some set containment proofs or some set equality proofs. And what we did last time is we talked about De Morgan's law for sets. And we used two styles of proof to do it. We did a proof by Venn diagram and a proof by elements. And I'd like to show you another way that we could do a proof in addition to those first two ways. So let's do a new example. This will be a set distribution. Okay, and what this says is that A union B intersects C is equal to A union B intersect A union C. Right? Now, there's a couple of ways that we could go about this, right? The two different proof methods. Let's start with a proof by Venn diagram, right? So if we set up a Venn diagram here, make it a little bigger this time. Here's A, B, and C. Okay. So what I'm looking for is A union B intersect C, right? So let me number these regions. 1, 2, 3, 4, 5, 6, 7. Okay. Which regions are going to be included in A union B intersect C? One, 4, 5, 6, 7. Okay. So all of A, right, which is 1, 4, 6, 7, and B intersects C. Well, B intersects C is 5 and 7. 7's already in there, so we'll just throw the 5 on. Very good. Okay, now let's find the regions for these guys. So what are the regions included in A union B? all except 3. Okay, so 1, 2, 4, 5, 6, 7. Okay, how about A union C? All except 2. Okay, 1, 3, 4, 5, 6, 7. And if I intersect those, what is that operation going to do to my list of regions here? It will come out the same as the left side. That's true. But what is sort of the behavior of this intersection operator to my list of regions? What is it going to do? Yeah, it's an and. It's going to pick out only the regions that they have in common. So they have 1 in common. They don't have 2 or 3 in common, but they do have 4, 5, 6, and 7 in common. And you can see that these guys are in fact equal, right? Another way of thinking about this is we can do sort of like a little highlighter situation. Okay, so let's say that I want to start out with A union B intersects C. Well, that's going to be A, all of A, right? Union B intersects C, so that also has this part included, right? Well, now let's do A union B intersected with A union C. So A union B, maybe let's do it with some slashes. Let's do it that way. So A union B, I'm going to do this way. A union C, I'm going to go that way, right? So A union B is this stuff, right? A union C is this stuff. And the cross-hatched section, that's what's containing both. And you can see that the crosshatch section is exactly the same as the highlighted section. Yeah. So there's another sort of more visual way of thinking about it rather than numbering all the sections. What do you guys think? Does that all make sense? Any questions? Yep. Okay. So let's try the proof a different way. So let's try it by proof by elements, right? So let's do proof by elements. By, if I can spell here, elements. Okay, now if we want to do a proof by elements and we want to show that 2 sets are equal to each other, what's sort of the large scale structure of that proof going to look like? So what's the definition of set equality? How did we define set equality last time? Yeah, good, David. We want to prove that one's a subset of the other and the other's a subset of the one. So we have to prove that this side is a subset of this one and this side is a subset of this one. And if we prove both ways, then we'll have it, right? So let's start with the first subset. So we'll say A intersect, oh, sorry, oh boy, A union, helps to write it down correctly. B intersect C is contained in A union B intersect A union C. Okay, cool. So now what we're going to do, that we have this containment, is we're going to assume that X, some arbitrary element X, is an element of the left side and show that it must be an element of the right side, right? So let X be an element of A union B intersect C. Okay. Now where do I go from here? Use the identities. Which identities do you mean, Brian? I'm not sure what you mean by that. Well, eventually we're going to use a distributive law. We can use a logical distributive law for and or. Yeah, but first we have to convert them. Yeah, that's exactly right. Good. So first we're convert, then we'll use the distributive law. So we'll say, okay, well, X is an element of A and X is an element of B intersects C. Oh, sorry, it should be an or, pardon me, for a union. Right? Okay, then we'll say, okay, well, then we have X is an element of A, or X is an element of B, and X is an element of C. Right? Now we can use the distributive law of or and, right? Because now we can say, okay, well, now we've got X as an element of A, or X is an element of B, and X is an element of A, or X is an element of C. Now what do we do? Should be equal to the right side. Okay, so how do I show that? Yeah, convert back the other way. Perfect. So now we have this or here, so we can convert this. X is an element of A union B, right? And X is an element of A union C. That's by definition of union. Then we have definition of intersection, right? So we'll have X is an element of A union B intersect A union C by definition of intersection, and that's what we wanted, right? That's the right side we were looking for. And of course, if you go the other direction, you start with this guy and you sort of just do the rule in the other direction, right? You say, okay, well, I start with this guy, I convert all of these things to logical symbols, then I use the distributive law for logic in going the other way, right? Going this way, and then convert back, right? Okay, so do you want me to do it the other direction? Would that be helpful? Or does that all make sense? Sure, perfect. Okay, so for the other way, we'll start off by saying A union B intersect A union C is contained in A union B intersect C. Okay, we'll let X be an element of A union B intersect A union C. Then we're sort of going to do the exact same sequence of steps, right? The justifications will be the same either way. So here, I can actually do this. Justifications are the same on both sides of the proof. So let's unpack the union. Oh, I guess I have to unpack the intersection first this time. That's okay. Union or intersection. Okay, either one of those two ways. So we'll say, okay, X is an element of A union B, and X is an element of A union C. That's by the intersection definition, right? Then we'll use the union definition and say, okay, well, X is an element of A or X is an element of B. and X is an element of A or X is an element of C. Then we use the distributive property to distribute out the X is an element of A part, and we'll get X is an element, oops, sorry, X is an element of A or X is an element of B and X is an element of C. Then we convert back. So we'll do the union first, say X, well, so now again, we want to do actually the inside of the parentheses first. We'll do this one. So say X is an element of A or X is an element of B intersects C. Make sure that looks round, not pointy, so we can tell the difference between the two symbols, right? And then lastly, we use the definition of union. Oops. There we go. Question on the left column. Should the second to last row split the parentheses by instead of or? Oh, wait, did I switch? Did I screw this up? Oh, this should be an and. Right, I wrote the wrong symbol. From the line above, that should be an and, that's an intersection. Yeah, I just made a typo. Thanks, David. Yeah, that's right. Cool. Yeah, thank you. Yeah, good catch. Okay, so let's try another one, right? You know, we could have proven this by, you know, by algebra, which is the final way. And proving something by algebra is using, where is my table here? Using this guy, right? This table of all the different set identities, right? And what I could have said is, well, it's true because of rule number 3, end of proof. But that's not a very detailed proof, right? So, so if we're going to do, excuse me, if we're going to do a proof by algebra, then it might be, it would be better to do a proof by algebra in a situation where it's not like one step where you say, oh, this is one of the rules, I'm done, right? It's sort of, you know, that's not a very good proof because it's not, it doesn't really explain the essence behind what's going on, right? You're just saying, oh, it's a rule, done, which doesn't really say much, right? If you go through a Venn diagram or if you go through proof by elements, that's describing what's happening with all of those different sets, right? So in that case, let's do a different case in which we can use an algebraic proof, right? So let me find a good one. Maybe we should, well, yeah, they don't really have a good one here. Let's do this. Why don't we do a couple of the exercises that have, oh, I see. Okay, those are in the next section. Okay, so in the next section, we'll be using algebraic proofs. Let's do a couple more proof by Venn diagram and proof by elements first. Okay, and then the next section, we'll be using those algebraic rules. Okay, so let's do this one. So for sets A, B, and C, A is contained in B implies A union C is contained in B union C. Okay, so our options here are to use either a proof by Venn diagrams or a proof by elements. Which do you think we should use and why? Implies might be confusing in the Venn diagram. Okay, yeah, maybe that's true. Right? How many sets would we need to use for our Venn diagram, do you think? Three, okay. And how should we arrange them? Let's see if that implies does get confusing or not. So if I'm going to make this Venn diagram, is it going to be, is it going to be this situation that we've been doing, the whole time? Yeah, A has to be inside of B. That's our premise, right? So really what we would want is we would want like a circle A to be inside of B. And then you said C is overlapping B. Is C overlapping A as well, or only B? It could overlap both. Good. And if you only had C overlapping B like this, then you're missing a sort of a possibility, right? Because it could be that C and A have some things in common, right? So to be the most general possible proof, I think you would want it like this, right? Because it could overlap both. It doesn't have to, but it could, right? Now I think we can examine our conclusion. Say, okay, well, we want to look at A union C. So A union C, let me use my, let's do it this way. So A union C, let's highlight. So here's A union C. And we want to know, is that contained in B union C? Well, here's B union C. It's the whole thing, right? So yes, it is. Right? So I think a Venn diagram does work in this particular situation. David, does that make sense? Yeah, still getting used to it. Absolutely. Yep, this is good enough for proof. You're done. Yep, absolutely good enough. Yep. So long as you have the right circles in the right places and the right colors in the right places, then yep, it's as good a proof as any. If you mess up where the colors are, then then it'll be wrong. so you can get it wrong, but I agree with you. It is easier than the proof by elements. It's not trivial, but it is easier, right? So let's see if we can do a proof by elements, right? On a test, yeah, absolutely. Yep, as long as you do it right. Yeah, I also prefer drawing. I think visual means of understanding arguments work a lot better for my brain than algebraic ways of understanding arguments. But again, that's just my brain. Like some people prefer the symbol pushing, and some people are visual learners, and it just depends on your style. Right? Okay. Yeah, I like them too. So okay, so let's do it. Let's do it the terrible way, right? So let's do it. So let's try the proof by elements. So where am I going to start in this one? On the left. Well, on the left of what? Like, what exactly are we assuming? What are we trying to show? The left of the implies. Okay, so what do we want to say then? So we want to say, there's some element inside of A and B. Okay, so you want to assume X is an element of A. Not quite. That's not quite how you want to start it. Remember, because you're trying to prove this. Trying to prove that this is true, that this set is contained in this one, given the fact that A is contained in B, right? So it's going to be a little bit different than what you thought. Yeah, good. You want to start with X in A union C, and then show that that has to be in B union C using this as part of our deduction along the way. Okay, so this is going to be one of our deduction steps, but we're going to start here, right? So we're going to let X be an element of A union C. Okay, let's translate that into logic, right? So that's going to say that X is an element of A or X is an element of C. Okay, by definition of union. Okay, so now what do I do? Well, not cases, not quite. Here's what we want to end up with. We want to end up with X as an element of B union C, right? So yeah, so now we use the left side, right? If X is in A, then X is in B. So if X is an element of A, we can conclude X is an element of B, or X is an element of C, since A is a subset of B. We can do that, right? Which means X is an element of B union C by definition of union. And that's the end of the proof. A little bit sneaky. That's why I wanted to show you this one, right? What do you guys think? Questions? Short and sweet. Yeah, this one's not that bad, right? Okay. Other questions for me? Okay, makes sense. Perfect. Looks easy. It's not easy, just looks easy. It's like juggling, right? It's like juggling chainsaws on a unicycle, right? Looks easy. It's not. Okay, so let's try another one. Let's try this one. Similar sort of idea. A is contained in B, but this time we're going to use one of our other operators, the power set operator. So say, in that case, the power set of A is contained in the power set of B. And this time, I don't think we can use a proof by Venn diagram, right? Because what is it to do a power set of a set in a Venn diagram? That's not really an option anymore, right? So I think in this one, we're going to have to do a proof by elements. Okay. Now it's going to be a similar structure to the last one. So where do you think I want to start? On the right, on the left-hand side of the right. Yeah. So what am I going to assume? Let what? Good. X is an element of the power set of A. Now, something I should have mentioned last time, but I haven't yet. It's implied that lowercase letters are elements and uppercase letters are sets. Now, if I have an element, something inside of the power set of A, is that thing that's inside of there, is that going to be a set or is it going to be an element? Yeah, set. Very good. Because the power set is a set of sets. It's a set of subsets, but it's still a set of sets. So if it's a set of sets, then what's inside of it? Well, sets. So let me use an uppercase X to indicate that there's a set inside of this power set. Okay. So what does that mean? So let's unpack this now, right? So we have this set that's inside of the power set. What do we know about it then? Not exactly, David. I mean, yeah, that's true. It is going to have, a size that's less than or equal to A, but that's not quite. I'm not worried about the size here. I'm worried about the contents. So what do we know about the contents rather than the size? The contents of X, that is. What's the definition of the power set? That's kind of what we want here. All the subsets. Say more, Sean. I'm not quite sure what you mean by that. Okay, X is a subset of A. Okay, so the power set of A contains all the subsets of A. That's true. And X is one of those subsets. That's true. Now, how do I say that? So you're right, but how do I express that idea? So I think, David, you hit it the closest, right? Yeah, X is contained in A, exactly. So if X is an element of the power set, that means X is a subset of A, right? That's by definition of power set. Is everyone good on that? Does that make sense? Okay, so what do I say next? Then we use the left, okay? So if X is contained in A and A is contained in B, then what do I know? X is contained in B, good. And why is that? By the transitive property of containment. And A is contained in B. Right? So if X is in A and A is in B, then X is in B. Okay, last step. Only one more step to go. We're almost there. Good. Well, almost. You almost had it. It's not X is contained in the power set of B. Oops, power set of B. We need a different operator in the middle. Yeah, element. Good. X is an element of the power set of B, right? If X is contained in B, then it's an element of the power set, which is exactly what we needed. We started off with something in the power set of A. We showed that that thing must be in the power set of B. So the power set of A is contained in the power set of B. What do you think? Look good? Questions? Okay, so cool. So we've done quite a few element style proofs. We've done quite a few Venn diagram style proofs. Let's do some algebraic proofs. Okay, these are at the end of section 6.3 that I'm pulling these from. So let's try this one. I have I'm just going to simplify the set here is my plan, right? So here's what I've got. I've got B complement union B complement minus A we take the complement of that whole thing. Okay. So let's see if we can simplify this thing, right? And what I'm going to be using it now is that table from section 6.2. So that table go. There we go. I'm going to be using this set of rules, right? These guys, to try to simplify this statement here. So where do you think I should begin? De Morgan's, okay? So we can take the complement and distribute it throughout. So I'm going to have B complement complement intersect B complement complement minus A quantity complement, right? I distribute the complement to both sides of the union and change it to an intersection. That's by De Morgan's. Okay, what should I do next? Yeah, double complement. So we can eliminate those. So we'll have B intersect B complement minus A quantity complement. That's double complement elimination. Okay, beautiful. Then we can De Morgan's the right side, almost, not quite yet, because set subtraction is not something that we can De Morgan's over. We can only De Morgan's over union or intersection. Luckily, we can transform this subtraction into a union or an intersection sort of thingy somehow. How do we do that? Yeah, it's the same thing as the intersection with a complement. If you take, x minus y, that's x intersect y complement, right? So now if I have B complement minus A, that'll be B complement intersect A complement. And then that whole thing has a complement on there, right? That's by definition of set difference minus. Okay. Now I can De Morgan's, right? So what do I get next on the inside here? So I have B intersect. And what have I got? B union A. Okay. That's by De Morgan's again. Okay, so now what do I do? Distribute, okay. So what am I going to get when I distribute? Remember, just like in logic, the outside symbols go to the inside symbols go to the outside. And then we'll use absorption in a second after that. But first, I want to distribute. So I'll say B, the outside goes to the inside. So I'll have B intersect B, inside goes to the outside, union, B intersect A. That's to distribute. Then I can do absorption. Or should I have done absorption? Okay, so this one's just B. B intersect B is just equal to B. So what's B union B intersect A? Is that just the absorption law? So let's look. Here's the absorption law. Sorry, bring this book over. Okay, so here's the absorption laws, right? We've got A union A intersect B equals A, or A intersect A union B equals A. Well, we have the A's and B's switched here, right? We have B intersect B union A, but it doesn't matter if they're switched, that's fine, right? I've still got something intersect that same thing union something else equals the original. So actually, I don't think I wanted the distributive property here. I think I could have just gone immediately to absorption and gotten that B out of it, right? So I can put everything back here. Okay, so I think that we should not have done distribution. We should have just said, well, this thing is just B by absorption. And now it's simplified. So this whole thing is really just the set B. Look good? Any questions on that one? Okie dokie. Let's try another one. We'll do one more of these guys. So we've got A minus A intersect B. That whole thing's intersected with B minus A intersect B. All right. So again, we're just going to try to simplify this a bit. Okay. So from here, where can I go next? What should I do first? Okay, set subtraction. So how do I translate that? So I'll have A, let me do the left side first. A, and the subtraction turns into what symbol? Intersection, okay, good. Then we'll have A intersect B, and then complement, right? That's going to be intersected with the same thing on the other side, B intersect A intersect B quantity complement. That's by definition of set subtraction. What do you guys think? Does that look good? Okay, so what do I do next? Associative. How's that? Never mind. Okay. And oh, and Sean, you said De Morgan's. Well, we could do De Morgan's, but there's actually a really sneaky shortcut we can use instead. What can we use here? Distributive law. Oh, I'm sorry. You said associative. That's exactly what we want. I'm sorry about that. That's not a, sorry, I was thinking distributive law. I was thinking that this was a union, but that's not at all what's happening. No, associative is definitely what you want. Yeah, sorry about that. That was Luan. Nope, yeah, you were right, Luan, because these are all intersections, right? We've got an intersection here and here and here. So we don't need any of these extra parentheses. All the intersections have the same precedence, right? So we can just say A intersect B complement, intersect B intersect A intersect B complement. That's by the associative property, right? We can just get rid of those parentheses because all the intersections have the same precedence. Okay, now what can we do? Yeah, I made the same mistake, Sean. I thought it was distributive too, but this is an intersection, not a union. Got to read it right. That's sometimes the hardest part is just looking at the symbols and seeing the right content. Yeah, very good. So we can use the commutative property to reorder items. So I can say, okay, I've got A intersect B intersect A intersect B complement intersect A intersect B complement, right? That's by the commutative property. And before I get quite to where you're at, Sean, I want to do a couple more things. Next, I want to reintroduce parentheses. Okay, so again, that's going to be the associative property, which is going to look like this. A intersect B, I want that by itself. Then I want this right-hand side by itself. Okay, now what can I do? This is the last step before your conclusion there, Sean. Yeah, the complement inside the parentheses, we just need one of them, right? We just need one of.
No,
go ahead.
You have A intersect B complement. You have like B.
Oh, I put it in the wrong spot.
That's what I was trying to say. Sorry.
Thank you.
No, because it's so hard to type all of those intersects out. I don't know an easy way to do that. Like upside down.
Yeah, you can use a caret.
A caret. Okay, sure.
Yeah.
Mm-hmm. But you can get rid of a set intersect itself is just itself. So you can get rid of A intersect B complement intersects A intersect B complement is just A intersect B complement.
Perfect. And what rule is that?
Identity. Sorry, I don't have them right in front of me.
Here, let me check because I don't have them memorized. No, it's not identity.
Complement. A intersect.
Well, it's intersecting the same thing with itself.
Oh, idempotent.
And that's idempotent. Yeah, that's right. Perfect. Okay, so I have A intersect B, intersect A intersect B quantity complement. That's by idempotent. And then the last thing is that the cancellation, right? So and which law would that be?
And that one is the complement law.
That's the complement law, number 5, right? If you intersect a set and its complement, you get out nothing. So that's the complement law. And that's it. So that's actually the empty set. Now this one, I think we can explore with a Venn diagram. Actually, let me pop up here. So we're supposed to get out nothing, right? And let's take a look at this. So I have two sets, A and B. Okay, and let's look at what we have on the left. So on the left side, we've got A minus the intersection of A and B. So which region is that? A minus B, yeah, it's just the left side of A. Because if you take A and then you subtract off the center here and get rid of that, well, all that's left is this side, right? Okay, what about the right side? Well, it's the same idea. Here we have B minus the intersection. So again, we have B without that center part. And what we're trying to do is find the intersection of yellow and pink. And of course, there's nothing that's shared by both. So that intersection is going to be empty right? Because there's no shared region from the yellow and the pink parts. What do you guys think? Does that make sense? You all happy with that? Yep. Okay. Cool. Well, let's do this. Let's take a short break before we get into section 6.4. Let's just take 5, get a snack, get a drink. We'll pop back and start into 6.4. See you soon. All right, so the last section in this chapter is section 6.4, and that's all about paradoxes, and in particular, Russell's paradox. So I'd like to start with a really simple example, and then we'll sort of work our way up to more and more complex examples here. So does anyone know an example of a paradox? One you want to throw out for me? What do you guys think? Yeah, the barber paradox. Okay, so can you explain it?
Yeah, so the barber paradox, it's in a town. Everyone gets a haircut at the barber, but if that's the case, like who cuts the barber's hair?
Almost. So in the
Almost.
town, everyone gets their hair cut by the barber, or excuse me, or they cut their hair themselves, right? So they either go spend money, go out and get their hair cut, or they do it themselves at home, right? And then you have the second part, right? Who cuts the barber's hair, right? Because if the barber cuts the barber's hair, then they're cutting their own hair. So they're not getting their hair cut by the barber. But if the barber cuts the barber's hair, then they're getting their hair cut by the barber, not by themselves, right? So either way you slice it, the sentence is false. Yeah, so if the barber cuts their own hair, that doesn't work because they're getting their hair cut by the barber. But if the barber cuts the barber's hair, that doesn't work because they're getting their hair cut by themselves. So it's false no matter what. And that really is the essence of a paradox, is it's a statement that's always false no matter how you interpret it, right? So that one's a little bit complicated because there's sort of two groups. There's the people that get their hair cut by the barber, and people that cut their hair themselves. And so I like one that's just a little simpler, is another example of a paradox, which is opposite day, right? And I used to like to think about this as a kid, right? So if today is opposite day, well, so opposite day is impossible, okay? You can never truthfully say today is opposite day. Why is that? Well, because if today is opposite day, and you say, oh, today is opposite day, well, that's not true, because if it was opposite day, you would have to say, oh, it's not opposite day, right? So that's if, so maybe I should write this down, right? So if I say today is opposite day, right? In the case when it actually is opposite day, right, then this would be false. Maybe I'll say this is going to be false, right? Because if it is opposite day, you wouldn't say it's opposite day. You'd lie and you say, oh, it's not opposite day, right? Well, what if it's not opposite day? Well, that just means it's a regular old day. And so if it's a regular day and I say, oh, today's opposite day, then that's also a lie, right? So it's false either way, and that's a paradox. Something like, if I know one thing, it's that I know nothing. Ah, that one's a little sneakier, right? Because if you know one thing, right, then you don't know nothing, right? But you also have a conditional wrapped up into there, right? Say, if I know one thing, then I know nothing, right? And that's definitely a paradox, right? Because, you know, if you do know the one thing, then you don't know nothing, right? You know something, right? And if you don't know one thing, you do know nothing, right? Okay. So there's also some other paradoxes here, the grandfather paradox and Zeno's paradox. Okay, so why don't you guys describe those? So Sean, what's the grandfather paradox?
The grandfather paradox is the time travel one, where you go back in time and kill your own grandfather, so then have to go back in time or whatever. I've heard it called that.
Sure. So that one is not a logical paradox exactly. Well, it's if you incorporate notions of time into your logic, then you can say that it's a logical paradox. But that's a that's a difficult philosophical enterprise to incorporate the notion of time into logic.
I always sort of took it more to be like a logical reason why time travel can't exist.
Right. I would say, well, so when you say logic, you mean reasonable. When I say logic, I mean ands, ors, nots, right? Conditionals and derivation rules, right? So,
Sure.
right, which is understandable. The common when people commonly say logic, what they mean is, you know, reasoning, right? But when I say logic, I mean, you know, I mean this, right? So you could create a formal logic that incorporates the notion of time, and then examine, you know, what's logically possible in this you know, sort of world, this environment that you've created, where you have formal understanding of time and logical principles. And you definitely could do that. And I think in that case, the grandfather paradox would exist. But that's hard, right? There are a lot of philosophers that think very carefully about time, and it's a pretty sticky subject, as the grandfather paradox illustrates, right? So yes, I do agree that that's a paradox, but I think it's not one that I can do this kind of an argumentation on, right? Does that make sense?
Yeah, totally.
Yeah. Okay. So Amber, what about Zeno's paradox? Oh boy. Okay. So someone in Atlanta wishes to walk to the end of the path, but before they get there, before she gets there, she has to walk halfway. But before she gets halfway, she has to go halfway to that, and then halfway to that, and so on, which requires an infinite number of tasks, right? Cool. Okay. So again, that paradox incorporates notions of space rather than time in that case, right? And again, that gets a little tricky, right? Now, it's a bit easier to incorporate space than time, I think, because, you know, mathematics is sort of geared toward exploring what distance means in terms of spatial distance, right? So we actually, I think, can resolve Zeno's paradox if you've completed the right prerequisites for this course. How do you resolve Zeno's paradox? It's not actually a paradox, that one. You take a limit. Okay, a limit of what? Yeah, calculus. Okay, good. So can you guys say more? How does that work? Yep, that always works. Forget the math and just walk. So why is it that even though you have to do an infinite number of tasks, you're still able to move? Certainly, if you had to walk 10 feet an infinite number of times, you wouldn't be able to do that, right? Because you have a finite lifetime. But somehow you are able to walk 10 feet total, even if you have to walk 5 feet, and before that you have to walk 2.5 feet, before that you have to walk 1.25 feet, and so on, right? You yourself are not bound by minute step size. Kind of. I mean, that's saying something really profound about the nature of spatial movement, which is that spatial movement is discrete rather than continuous, right? Like if I move my hand like this, am I moving, you know, in little chunks, like little, little halting steps, or is it just like a smooth motion as I move my hand, right? So it, and physics is not clear about that. Sure, there's a Planck time, so you can argue that it's discrete in terms of the amount of time that you take. And you can also argue about Planck length, and I shouldn't get into all that. That's a bit beside the point. The point is that we're not really sure if that's a discrete, smallest unit of measurement, right? In some ways it is in physics, and in some ways it's not. So, but we shouldn't go too deep down that rabbit hole, right?
So to resolve Zeno's paradox, you take like an infinite sum basically of like terms that are halved each time or whatever, and you do end up with a finite answer.
Right. Okay. So that's
And that's what the calculus gets us.
Yeah, that's the ticket, right? You're doing an infinite number of things, but as you do each thing, it's not a constant amount that you're moving. It's a decreasing amount that you're moving, right? So if I have, from 0 feet up to 10 feet, right? You say, okay, well, first I'm going to go halfway 5 feet, but before that I have to go 2.5, and before that I have to go 1.25, and so forth, back this way, right? Well, here's step 1, and before that you have to do step 2, and before that step 3, and so forth, right? But these steps that you have to do, they're shrinking in length, right? So the reason why, even though you're doing an infinite number of steps, the total amount that you move is not infinite, is because each step is shrinking in the amount of length that you have to move each time, right? Now, it may be that the fundamental nature of space is finite or continuous. It doesn't really have bearing on this particular problem, I think, right? Because if you go, even if space is continuous and there are an infinite number of steps you need to make, that's still okay, right? Because the very first step that you make is infinitely small, right? So it happens infinitely fast, right? Because it's what's called an infinitesimal, right? Infinitesimal distance that you're moving, right? And so the reason why you can move is because those steps, as they go, back down to 3, 4, 5, 6, etc. Those steps get smaller and smaller as you go, right? And they get small fast enough that when you put them all back together into the grand total, you get out a finite result. And that's where the calculus comes in, right? The calculus, the whole, not the whole point, but one of the purposes of calculus is to analyze the rate at which your step size is shrinking. And then to say, well, does that limit converge, right? So as we add together, right? As we add together from I equals 0 to infinity, the step size, which is 10 divided by 2 to the ith power, I guess that would be from I equals 1 to infinity, right? Right? That just equals 10. Right? Or if you want to put the limit in there, if the limit makes you happy, let me turn this into an n, right? So the limit as n goes to infinity of this guy equals 10. And why is that? Well, because you can factor the 10 out, right? The 10's not part of the sum. You remember this from last term, right? So you factor the 10 out, you get this limit as n goes to infinity of the sum from I equals 1 to n of 1 over 2 to the I, 2 to the I times 10 equals 10 times 1 equals 10. Because we already showed last term what that particular limit is equal to. And the reason why this limit converges to 1 is because this sequence, right, this series rather of terms that we're adding together shrinks fast enough that it converges to a finite result, right? And if you had some other kind of rate at which you were decreasing, it may or may not converge, right? If you did 1 over 3 to the I, well, that would still converge. But if you did 1 over I, that would not converge, right? So it just depends on how quickly this range is shrinking. As for Zeno's paradox, it does converge, and Zeno's paradox is not really a paradox. It's a misunderstanding of the limits of convergence for sequences, right? Is because they hadn't invented calculus yet in 500 BC, right? So they didn't really get it. In fact, all of Zeno's followers thought that movement didn't exist because of that paradox, right? They thought that because of this thing, there is no such thing as movement. It's not really real, which I think is quite a faulty argument, right? Reminds you of work done with directional fields. What do you mean by that, Tamara?
It's kind of hard to explain, but it just reminds me of that because it's all in one, it's all aimed towards one path, but you could say that there's like teeny tiny movements all along that path. It just reminds me.
Oh, okay. I see. Sure. All right, great. So we looked at a couple paradoxes. We had opposite day. We talked about Russell's paradox and Zeno's paradox and the grandfather paradox. Your book is going to focus more on the logical paradoxes rather than on, spatial or temporal paradoxes. So let me see if I can reframe Russell's paradox in terms of the set notation that we've been using, right? So basically what we're saying with Russell's paradox is the Barber's paradox, right? So this guy, Bertrand Russell, came up with the Barber's paradox a little over 100 years ago to try to explain this issue with set theory, actually. So let me, show you the notation here. So what we're concerned with is a set of items that's defined in the following way. It's a set of other sets contained in some universe, right? So subsets of some universe, such that the set does not contain itself. Okay. So let's see if we can trot through the paradox, okay? So S is going to be a set of sets, and these A's, the things that, together build up S, those are also sets of sets. So S is like a set of sets. Okay, so it's a little complicated, so let's go through it slowly. We're concerned about all of the sets in some universe that aren't elements of themselves. It's not necessarily the power set of the universe, because the universe might consist of sets already. The universe doesn't have to consist of simple elements, right? The universe could be anything you want, right? So we could have sets of sets already sitting in the universe. Does that make sense, David? So we don't have to incorporate the power set here. Yeah, so they will be nested sets. That's exactly right. Right? So let's trot through the paradox. I think this will help, right? Let's think about if S is an element of itself, okay? Because we're doing sets of sets. So maybe S is one of the elements inside of itself, okay? Is that possible? Yeah, David, we're getting to that recursive set idea, but it's going to be just a moment, right? So is it possible for a set to be an element of itself, for this S to be an element of itself, given its definition right here? What does it mean to be an element of S? By definition, what does it mean to be an element of S? Okay, you're a set in the set of sets of the universe. So you're something in the universe, but you're not S itself. Not quite. That's not quite it. Okay, so if a set is an element of S, then it does not have itself as an element. It doesn't contain itself. It doesn't live inside of itself, right? So what we're saying is, okay, what it means to be an element of S is that you don't live inside yourself. So can S be an element of S? No, right? Because if S is an element of S, that means that it is inside of itself, right? But the definition here says it's not, right? So if S is an element of S, what does that mean? That means that S is not an element of S. Contradiction. Okay, let me go through that one more time, okay? What it means to be an element of S, right? What it means to be inside of S, let's say X is an element of S, means X is not an element of X, right? So what does it mean for S to be an element of S? Well, that means that S is not an element of S. But of course, that's a contradiction because we're saying, hey, S is inside of itself, and here we're saying S is not inside of itself. Well, those, you know, if true implies false, that's a contradiction, right? Well, what about the other way? What if S is not inside of itself? What does that mean? Then it will be an element of S. If S is not an element of S, that means S is an element of S complement. What is S complement? Well, X is an element of S complement means X is an element of X. I should make these capitals because they're sets, right? So that's a contradiction too, right? If it's not an element of itself, that means it is an element of itself. Also a contradiction. It's a contradiction either way, and with these two contradictions together, that's a paradox. What do you guys think? Is it too self-referential to make sense, or are you guys getting it? What do you guys think? So it's trying to finitely describe the universe in set notation. I'm not quite sure what you're asking there, David. It's pointing out a problem with what sort of collection we allow sets to be, and that's exactly it, Sean. Yeah, that's very very insightful. When Russell came up with this is the Barber's paradox, by the way. So maybe that'll be a little bit helpful. Okay, the Barber's paradox says, okay, there's a town. Here's the town. Okay, everybody in the town either cuts their own hair or gets their hair cut by the barber, right? So here's the town, all the A's, these are the people in the town, right? They either cut their own hair or they get their hair cut by the barber. Now the question is, what about the barber? The barber is S, right? Is the barber in the set of people that cut their own hair or in the set of people that get their hair cut by the barber? And no matter which way you go, right? Sort of like opposite day, same thing. No matter which way you go, it comes out false, right? So the Barber's paradox was meant to explain this situation with sets, right? So So this is pushing the limits of what we can describe. That's true. And the problem here, at least the way that Russell saw it, is not with the paradox, right? The problem is with S in the first place. Russell's idea was there can't be such a thing as a set like S. And that's not a bad idea, okay? Let me show you why. What is S, okay? S is the set of all things in the universe that don't contain themselves, right? So let's try to do an example. How about that? Okay. If S equals 1, 2, 3, or sorry, pardon me, let's do A. If A equals 1, 2, 3, is A an element of S? Is the set A an element of itself? So this should be an easy question. Is the set 1, 2, 3 an element inside of the set 1, 2, 3? No, right? The only thing that's inside of this is 1 or 2 or 3. The set 1, 2, 3 is not a part of it, right? No, A is not an element of A. So I'm sorry. So my bad. This would be a yes. Pardon me. That's a yes. Yes. Okay. So A would be an element of S because it's not an element of itself, right? Okay. So let's try another one. What about B? Okay. So B is this set, 1, 2, 3, and the set 1, 2, 3. So now B is a set of sets, okay? Is B an element of S? Yes. Why? Because it doesn't contain B, right? This whole thing is B, right? That whole thing. And that whole thing doesn't occur inside of B. Only a part of it is listed as a new element, not the whole thing, right? So yes, B is not an element of B. Okay. Because a set can never contain itself. Well, I wouldn't say that. What if I do this? What if I say C equals 1, 2, 3, C? Is C an element of S? What do you think? Good. No. Because C is an element of C, C, by definition. And now you guys have hit the rub, right? And this is what Russell was thinking about, right? Well, what the heck is this thing, right? This thing where it's a set that has itself inside of it, wouldn't it be infinitely large, or does it only have 4 things? Well, both, kind of, depending on how you look at it, right? Let's see if we can unfold this. This is going to be equal to 1, 2, 3, and the set C. And what's the set C? Well, the set C is 1, 2, 3, and the set C, which is what? 1, 2, 3, and the set C, right? And if you have a C on there, like if you just stop, right? I'll just stop right here, C. Well, I still haven't defined C, right? This is correct, but it's not complete, right? Because I've got 1, 2, 3, and then another set of C, which is 1, 2, 3, something, and then another set of C, which is 1, 2, 3, and then a C on there. But as long as I have a C on the right-hand side of this definition, it's not really a complete definition, right? So I would say, in some sense, it's got 4 things in it, and in another sense, it's got infinite things in it. Yeah, the expansion is the issue. This makes what's called an infinite regression, right? Or an infinite recurrence. And what that means is it just keeps looping on itself forever. It's like an infinite loop, right? And it keeps on having more and more stuff in the set, which makes an infinitely large set, which is fine, right? That's not necessarily problematic. I mean, we have the natural numbers. That's an infinitely large set that we're happy to work with. So no big deal there. But the natural numbers have quite a different structure. There's not this nesting of sets inside of sets in the natural numbers. It's just a regular old set with elements in it. There's no nesting at all, right? And so then the question becomes, okay, well, these sets of sets, are those even okay? Should we even allow there to be sets of sets? Like, is that, you know, is that a reasonable thing to do mathematically, or is it, you know, a bad idea, sort of like Zeno's paradox, where it just doesn't really make any sense, right? Or is there a way that we can develop and expand mathematics to make sense of this sort of arrangement, the way that calculus made sense of Zeno's paradox up here, right? So there's some questions in the chat. Would C have a different cardinality than the natural numbers? That's a good question. I would say the cardinality is 4. But I think we'd have to look really carefully at the definition of cardinality. And I think, you know, we'd have to look in your book and see what that definition is, and then follow that definition very carefully to see whether this particular monstrosity is included or excluded from the definition, right? Yeah. Okay. Let me give you another example in case this is a bit too esoteric, right? Maybe you've heard of the GNU folks, right? They do Linux programming, right? Does anyone know what GNU stands for? Yeah, GNU's not Unix. GNU, right? But GNU is part of the acronym is included in the definition of the acronym, right? It's called a recursive acronym. So what does this mean? Well, this means GNU, not Unix, not Unix. Right? Yeah, right. So yeah, so people that use the acronym and then say the words in it are very frustrating to those particular English-minded folks among us, right? Like saying your PIN identification number, right? Okay. So so maybe this helps a little bit. You can see sort of the same things happening with trying to expand the GNU acronym that is happening with this recursively defined set C. That's why they named it that, to be sarcastic, right? Cool. Okay, so what do you guys think? So let me pause here. Do you guys have questions about all this stuff? Or is it making sense? How are we doing? It does have the tenor of a joke, I agree. But it turns out that it's not just a joke. It actually is really important and profoundly meaningful, both to the truth of mathematics in the universe and to the operation of computers that we build and program. Yeah, that joke ruined Bertrand Russell's life. Yeah, so the way the story goes is old Birdie he did not like this. He thought, oh, this is gross. Like this whole thing expanded forever. This is real nasty. Like this is terrible. We shouldn't allow this to happen in math. Like this is just awful. And so he got his buddy, Alfred North Whitehead, and him wrote thousands of page math book called the Principia Mathematica, which created a whole system of different levels of sets and which sets could be included in other sets. And you can't, in his system, in their system, I should say, you can't have a set that's included in yourself. You can only include a set from a different level inside of another set. And so you exclude this possibility of a set being inside itself, right? You can't put C in here. You could put a set from a different level in here, but if you do that, then you've excluded this infinite regress, right? And so Russell tried to solve this problem by saying, okay, well, we'll make these different levels of sets, and you can only include a different level, not yourself, and then we won't have this paradox. He spent 10 years writing this book with Alfred North Whitehead, okay? And the idea was that he was trying to say, okay, well, you know, we can eliminate these paradoxes from mathematics so that, you know, paradoxes won't ruin our ideas and our, you know, our means of understanding the mathematical world. But it failed, right? After that 10 years of work, a few years later, a fellow named Kurt Gödel came along and used Russell's paradox to prove not only that the paradox is useful and important, but also that mathematical truth is necessarily incomplete, okay? If there's a mathematical system that you claim you can understand truth, or you can prove true things with your mathematical system, then what Gödel's theorem says, Gödel's incompleteness theorem says, is that there will be true statements in your system which are by definition unprovable. So let me say that one more time, okay? If you assume that you build a system like Russell's, where you have this whole system of these different levels of sets and, you know, different rules for how sets can interact with each other and so forth. So you build this whole system like Russell did, okay? If you do that, then there will be true statements in your system, logically true statements, that are by definition unprovable. You know that they're true, and you know that you can never prove it. And he used Russell's own paradox to make that argument, right? So he destroyed all of Russell's work with Russell's own argument, that's the joke that ruined Russell's life. Very ironic story, right? And Gödel's incompleteness theorem, along with the halting problem, which Turing came up with, which we're going to talk about in just a minute here, formed, you know, the foundation of modern set theory and theory of computation. Okay, so, and everyone should go read Gödel, Escher, Bach, because it's awesome. I completely agree, and I also endorse that you all read GEB. Man, it's a great read. It's very weird, but you should definitely check it out. It's pretty fun. His sequel, I Am a Strange Loop, is also pretty interesting. This guy Hofstadter, who's a recent philosopher in the past few decades, argues that human consciousness is a result of sets being included inside of themselves, and that mathematical idea is a good way of understanding like the true essence of human consciousness. So interesting stuff. Yeah, pretty cool. Another for the list. Yeah. The sequel is a lot easier to understand than the first one. The first one's a pretty tough. There's like exercises, like there's math problems in the book that you're supposed to do as you read, right? The sequel, I Am a Strange Loop. Right, that one does not have exercises. That one's a bit easier read. Quantum computing sense Democritus. Yeah, I didn't even know about that one. Who's that one by, Sean? That's quite a catchy title. Scott Aronson. Okay, cool. Yeah, nice. Yeah, Democritus is a fascinating character. We talked a little bit about him last term. Yeah, okay. I'll put that on my list. How about that? Cool. Oh, we got canceled. Oof. Yeah, well, mathematicians aren't not necessarily the most socially aware human beings in the world. Unfortunately, does not surprise me. All right. So going a little bit different direction. Let's talk about the halting problem, okay? So this idea of paradox that we've been chatting about, where you have opposite day, Russell's paradox, the sets that contain themselves. Okay, so this guy Gödel made up what's called the incompleteness theorem, which says that in any mathematical system, there are true but unprovable statements. Alan Turing took the same argument and came out with a different theorem for computer science rather than for math. But the essence of the argument is the same. It's still got Russell's paradox as sort of the essential part of the argument. And so let's talk about that, right? Can someone describe the halting problem to me? Does anyone know what it is? Want to give me a short description? A program can't debug itself. Perfect. Yeah, that's really great. That's a very good way of putting it, right? Let me be a little bit more precise to the halting problem. Although you're absolutely right, David. I would say a program can't tell if it can stop running, right? Which is debugging in a sense. Like if you have an infinite loop in your program so that your program never gives you output, that would be a bug, right? And so it's a particular kind of bug that we're talking about here. And the bug is, does your program have an infinite loop that makes the program hang forever, right? It's just like sitting with the wheel spinning and you never get your answer out, right? And that is important. I just want to be clear, like if you have a computer program and you want to know if your program works, well, okay, sure. So you test it. So you run your program, and you're sitting there waiting, your cursor is blinking, and you don't see an output, right? What would be really nice to know at that point in time is, hey, how long should I keep waiting? Like I'm running my program, the cursor's blinking, I'm waiting to see if it's going to output the right answer, and I just keep waiting and waiting and waiting. It's been 5 minutes, 10 minutes, an hour. You come back, check on your program, cursor's still blinking, still no answer. What would be really nice is if you could know if your program has a bug in it or not. Is it just that your program takes a long time and that's why it's taking an hour because it's doing, billions of calculations? Or is it that there's an infinite loop in your program and you're never going to get an answer and there's a bug that you need to go fix, right? So what would be nice is if you could take your computer program, feed it to another computer program. We'll call this other computer program the Oracle, okay? And the Oracle is going to prophecy this answer for you of, hey, is your computer program going to run forever because it's busted? Or is it going to eventually give you an answer that you're looking for, right? And the halting problem, what Alan Turing came up with, is he proved that building such an Oracle is impossible. And it's impossible because of Russell's paradox, okay? So let's go through how that would be, okay? So this Oracle that I was talking about, let's formalize this with some notation, okay? And this is called the halting problem. Okay, so here's my Oracle. It's called halt. And I'm just going to describe it as a function, okay? So halt takes two things. It takes your computer program, P, but it also needs the data that program was running on, D. Why is that? Well, for some programs, with some data, they run forever, and with other data, they stop. Halt means stop, right? So this is what this is supposed to tell you. This is supposed to be true or false, right? Does this program halt on this data? Yes, or no, does it not halt on the data? And that depends on the data, right? So let's say that our program is here's our program. P of D is, let's do this. It can do two things. It'll output 0 if D is greater than 1, right? And it'll loop forever if D is less than or equal to 1. And you can imagine a program that did that. What if the program looked like this? We have a while loop, right? And we say, okay, we'll have our, int, here's my program, int var equals 0. I input into my variable, right? And then I have this while loop, and the while loop says while var is less than or equal to 1, var minus minus. Cout 0. Okay, so there's my program. Now, if I input a 1 into here, what's going to happen? Well, 1 is less than or equal to 1. So it's going to subtract off of my variable and loop over, which is going to make var even smaller. So it'll keep looping over and over and over, right? But what if I put in 2? Well, 2 is not less than or equal to 1. So I skip the while loop entirely and just print out that 0, right? So are y'all happy with, this program being a C++ implementation of that function? Is everyone with me on that? Any questions? Does at least that part make sense? Okay, that part makes sense. Cool. Okay. So we have a program. It runs on some data. That program may or may not halt, depending both upon the program and upon the data that you feed to that program. Cool. Okay. So here's how my halting function is going to work. Okay. Halt of a program running on some data is defined as follows. It's going to print out H if the program running on that data halts, and it'll print out N for no if the program run on the data loops forever. Okay, that's my definition of halt. People still happy with the notation? Okay. Let me define another function for you. This one's called test. Okay, and the way that test is going to work, it's only going to take one input called x, and it's defined in terms of the halt function. So here's what it's going to do. It's going to loop forever if halt xx equals h. And it's going to halt if halt xx equals n. Okay. So what test is doing, it's taking one input, and that input's going to be the program and the data. Okay. Now you might be a little bit concerned here. You might think, well, how could you have the program and the data being the same thing, right? Well, what is a program and what is data, right? Or let me phrase it a different way. what's an input to a program versus the program itself? They're both data. They're all just ones and zeros. It's all just binary, right? This whole program, its representation in your computer is just binary. What about if I input the number 2 as the data? Well, that's just binary. It's just the number 1, 0. So the whole thing's just binary. You could take this whole program, this whole thing, which is some large binary number that's stored in computer memory, probably hundreds of, or even thousands of bits long. Okay, fine. And you could use that program, that 1,000-bit binary number, and use it as your input. That's fine. What would happen if you did that? Well, if it's a really big number, then that particular input to the program's own text as the input to the program would cause it to halt. So if we took this program, let's call this program, I don't know, let's call this program Y. Okay. If I did test of Y, what would happen? Okay. Well, what I'm going to do is I'm going to look at halt of YY. And what's going to happen there? Well, I have this program Y. P, that's my, the first thing, P to my halt function, that's the program. The data is also going to be Y. And if Y is equal to, 1 0 0 1 0 1 0, this like 1,000-bit long binary number, right? And I plug that in for var, well, that's definitely going to be bigger than 1, right? Because it's this huge number, right? So the while loop won't happen. It will print out the 0 and it will halt. So halt YY is going to equal H. It will halt, right? And what happens in that case for test, that implies test of Y. Well, let me just come up here. Test of Y, since the halting pops out H, it'll loop forever. Yeah? How you guys doing? Still following? Questions? Following. Awesome. Okay, we're almost there. We're at the last step. Okay. Last step is running test on itself. Here's the recursive part. Okay. Now what's going to happen? Well, test running on itself, what's it going to do? Well, we're going to have this thing gives us this equals, let's say, halt of test on test. Right? Because you take whatever's in here, and here we got the Y, and that just becomes both arguments to halt. In here we have test, that becomes both arguments to halt, right? Because whatever you put into here, test, that's what becomes both arguments to your halting function. Now, what does this mean? Halt of test on test. Well, there are two options. Halt of test on test would give us an H if test, test, let me just start over. Gives us an H if test of test halts. And it'll give us an N if test, I did it again, test of test loops forever. Okay, so halt of test on test gives us an H if test run on test halts, gives us an N if test run on test loops forever. That's what halt is going to do. What is test going to do? Well, test That's going to loop forever if we get out an H, right? So test, if we get an H, that means we loop forever. That's the definition right here, right? If we get an H, we loop forever. If we get an N, then we halt. Does anyone see the contradiction? It will never stop. I'm not quite sure what you mean, David. There we go, Sean. It does stop, in which case it didn't stop, or it didn't stop, in which case it did stop. It's the exact same thing as this guy. If it is opposite day, then it's not opposite day. But if it's not opposite day, then it's not opposite day, right? You have these two options, right? And either way, it comes out false, right? So what do you guys think? Does that make sense? If we get this H, that means it loops forever, right? But if we got an H, that meant that it halted. So, and you can't loop forever and halt at the same time. They're opposites, right? Or if you halted, what does that mean? Well, that means that you looped forever, which is also impossible. What do you guys think? Questions? So the theoretical program can say if it halts. Yeah, the theoretical program could say if it halts, right? This theoretical program called halt will tell you whether or not another program halts. What we did is we used this program to build another program called test, which does the opposite behavior of its halting counterpart, right? So this test program, maybe I should have called it opposite or something like this, right? It does the opposite of what halting says it would do. And because we've set it up to do the opposite, that creates a paradox, right? You say, okay, well, if this thing halts, then don't halt. If this thing doesn't halt, then do halt, which will always be the opposite of what it was supposed to do, which is what causes that paradox, causes that contradiction, right? And again, this might seem really esoteric and weird, and it is both of those things, okay? So don't get me wrong, this is really weird, but it is true, okay? It's formed the foundation of modern mathematics for the last 100 years, okay? And theory of computation as well, right? So a lot of people have thought about this and tried to figure out what it means and how it works over the past 100 years. And it's still true and still standing as much as it was 100 years ago, right? So even though it's weird and terrible, like a lot of things in this class, it is true, right? And it's important and meaningful because we can't make this program called halt. It's impossible, right? You also can't make programs that can debug other programs, right? Because if you can debug them, right, that's the same sort of thing as being able to tell if it'll halt or not, right? You also can't tell if a program will give you some specific output, right? Because you can run this kind of argument, right? You also can't tell if a program is the same, right? Will give you the same set of outputs for the same set of inputs as some other program, right? Because you can run the same kind of argument. So you can't simplify, you can't look at two programs in general, say program 1 and program 2 and say, hey, are these programs the same, right? Are these going to give you the same output no matter what input you put in? Can't tell that either. That would be nice because maybe you could, you have a super long program, millions of lines long, and you find a much shorter version that's only a few thousand lines long. You say, hey, well, are these programs actually the same, right? Of course, you can't really beta test that because there would be an infinite number of things to test. You can't really analyze it logically because you can't analyze a program with millions of lines in it logically. So that option's out. And all you could really do is have another program check for you. but that program can't exist. So you're SOL, right? You can have an AI that learns by itself. That's a different thing, right? So AI learning does not fall into this trap of the halting problem. That's a different sort of thing. And David, you're thinking machine learning stuff too. So I didn't get that impression. So why did you jump from that to AI? It's about knowing things. I'm just a little confused why you would have thought. Oh, in the movies. Okay, sure. Well, movies are generally not very accurate. Okay, so the technical truth of this is that this kind of an argument doesn't really have much bearing on artificial intelligence. They're two sort of separate sorts of things. Now, Turing was involved in both. So that actual guy, Alan Turing, developed both ideas about artificial intelligence and the theory of computation. But the two aren't really very closely related, I would say. Yeah, they're different sorts of things. I mean, so here's the issue, right? People wonder, hey, well, can I make an AI that could do this, right? Can I make an artificial intelligence that can look at a computer program and say, hey, does this thing halt or does it loop forever? And that's where the intersection is. Or can a human, right? Well, I think a human can sometimes, and the same is true for a computer program, right? Can a human tell if a computer program that's trillions of lines long, can a human figure out if that's going to halt or not? No, of course not, right? And could a computer do that? No, probably a computer couldn't do that either, right? What this is saying, here's the sticking point, right? Is that this is for any program with any data. This halting program needs to work on any program whatsoever, no matter how long it is. Could be a trillion lines of code or a quadrillion lines of code or a Google lines of code, right? More lines of code than atoms in the universe, okay? Doesn't matter how long it is, it'll still work, right? And that's not usually what people think in this argument. They think, oh, I have a program like this. Can a computer look and see if this is going to loop forever? Yeah, of course. This program's like 5 lines long. It's not that hard to understand. You could look at it with your eyes and be like, oh yeah, it'll loop forever sometimes, and sometimes it won't. And it'll depend on the value of var. Certainly you can look at this particular program and tell me that, as could an artificial intelligence system could probably figure that out too, if it was smart enough, right? But that's not what this is saying. This is saying for literally any program at all whatsoever, billions of lines long, and the data, which could be billions of data points that you plug into it, then can you tell if it halts or not, no matter what? And the answer to that is no, that's impossible, right? Does that distinction help a little bit? There's some questions in the chat about a spectrum of correctness statistically that's not discrete, that wouldn't have bearing on AI. Ooh. Yeah, so I'm not quite sure what you're getting at, David, but Sean, your sentence is true. The halting program either works or it doesn't, and in fact, it doesn't. That's true. But David, I'm not sure what your question is. Does that response address your question there, David? Okay, it does. Okay, great. So that's a little bit about the halting problem. We're going to circle back to this idea of paradox next week when we talk about the little food for thought I gave you last time, which was the size of the power set of the natural numbers versus the size of the natural numbers. Here we're talking about sets of sets, right? And so you might think, oh, well, this is the exact kind of example where this argument about sets that contain themselves would be relevant. And in fact, you're right. So Russell's argument here about sets that contain themselves actually came from another mathematician by the name of George Cantor, who is thinking about this problem maybe 20, 30 years before, back in the late 1800s, okay? So the answer to this question about the size, these sizes of infinity, right, are going to have some interesting parallels with the halting problem and Russell's paradox that we'll talk about next week. Oh, and one more in the chat here. You were thinking about needing an external source of validation. There needs to be an external perspective. The system cannot ultimately fix itself because it's turtles all the way down. Yes, that's right. So the problem with thinking about a program that can tell you things about other programs is that it all breaks down when you feed that program to itself, right? When it's that self-reference that breaks the whole thing, right? Yeah, so that's a good way of saying it, David. Yeah, that's right, Sean. Yeah, this is a different kind of infinity than this one. And it turns out there are different sizes of infinity. We're going to prove that next week. But in the meantime, we have about a half hour left. So let's talk about the lab. And for that, let me stop this guy. Pop over here. Let me get my chat and my participants open. Good. Oh, and let me show you where I got this code from. So I got this code from here in the assignments. Under lab 1, I have some code ready and waiting for you. If you had me last term, we're going to be doing the same sort of thing. But for the new people that haven't had me yet, the basic idea is you go into the lab. I got some code here for you. Here's some instructions, right? Get OpenGL up and running. You can use the boilerplate code I attached to test your compiler and make sure that everything's correctly installed. Or you can run the code from the Linux server or from Visual Studio. Or you can run it from Xcode as well if you get Visual Studio set up on OpenGL set up on Xcode, right? Once everything's working, attach your CPP code and a screenshot of the graphics window with a shape inside. And here's what the shape that you should make. You should draw a 3D version of the first letter of your first name. Okay, so remember, we're going to be doing 3D graphics, right? So if the, I would make a 3D N for this first lab, okay? Recall that you should draw inside a 3D box with a range of -1 to 1 in each of 3 dimensions, which I'll talk about in a minute when we go through the code. And to do this, you'll be editing the draw object here function using these guys to draw your shapes, okay? Yeah, you can run this on the Linux server. It's just going to be really, really slow. So I would suggest using either Visual Studio or Xcode this term because the 3D graphics are just really painfully slow from the server. So yeah, so I would recommend doing Visual Studio or Xcode. Now, how are you going to do this? Okay, I have this file here for you, boilerplate.cpp. And what I've done is I've set up this project that has OpenGL libraries included in it. And you can see all about how to do that in the discussion post here. Sorry, not discussion post, announcement here. How to use OpenGL in Visual Studios. There's a YouTube video and all the files you need are in this zip file here. Download this guy, watch the video, and you can set up a project, right, to which you would add an item, which is that boilerplate code that I included in the lab. Once you get there, here's what you get. All right, so starting from the top, I have some notes here from how I built this thing. I got some include files, so I'm including the OpenGL utilities toolkit and some math in case we need any math functions. I've got some global variables and constants, okay? So I've got my refresh interval because this thing is actually going to be animated. So the speed of the animation is controlled by this constant called mils, which is the number of milliseconds between each frame being drawn on the screen. I also have a zoom, an X angle, and a Y angle, and an array of Booleans called keys, okay? Now what's going to happen is I'm going to be able to press the keys to move my, my 3D object around, because it's not really that fun to look at a 3D object without being able to move it. That's kind of pointless, right? Then it's kind of 2D, right? So we actually want to be able to move this thing around. Let me run this for you and show you how it works. And I think that'll give you some insight into the code. Okay, so here it is, right? There's a donut and a sphere. And what I can do is I can use the keys on the keyboard to move this thing around, right? Back and forth on the y-axis, back and forth on the x-axis. And I can also zoom in and out, right? So I, J, K, L are to move this thing, and then X and Z are to zoom in and zoom out. What do you guys think? Does that make sense? Yeah, so there's quite a few new functions in here I want to chat with you about, okay? So maybe the first one, let's talk about the keyboard input, because that's a good one to chat about, okay? The check keyboard function keys down and key down and key up, okay? So what this is doing, saying if keys of X, right, then zoom out. If keys of Z, then zoom in. If I, J, K, or L, then you can either rotate up, down, left, or right. And what's happening is we have this key down and key up function. And what we do is that these functions, key down and key up, are called in a loop by OpenGL every 20 milliseconds, okay? And what those functions are doing is they're modifying this global array that's keeping track of key presses, okay? So in the key down and key up functions, what they're actually doing is they're saying every 20 milliseconds, hey, is there a key that's being held down? If so, go to the key array, to that particular key, and say, true, yes, that key is right now, is being pressed right now. Maybe 60 milliseconds later, you let go of the key. Okay, well, in that case, the key comes up and you would change our keyboard array to false. Now, what's going to happen is anytime that the X location in our keys array is true, I'll zoom for that duration. And as soon as I let go of the key, then this location in our keys array will become false and I won't zoom out anymore, right? And the same thing for X angle and Y angle. So what's going to happen here when I run this is as long as I'm holding down the J key, it's going to rotate left. As long as I hold down the L key, now I let go and it stops, right? And I can actually do multiple things at once, right? This way I'm rotating up and left at the same time. I could also zoom while I do this, right? So in this way I can, do multiple things all at the same time. Yeah. Okay, so that's the input. Let's talk about the output for a minute. Here's the output. Draw object here. Okay, look what I've got. I'm setting up a color. Okay, it's 001. So what color do you think that is? Close, yeah. So black, black, white. And why are there 3 arguments there? What are these 3 arguments indicating to the color? Yeah, red, green, and blue. So what color is this going to be? If I have 0 red, 0 green, and full blue, it'll be blue, right? And so next, after setting the color, what I do is draw this sphere, right? So my sphere should be blue, right? Okay, what about this? What's this color going to be? White, good. And so my torus, the donut shape, that should be white. Yeah. So if I run it again, I should have a blue sphere and a white donut. And there you go. There's my blue sphere and white donut. Okay, cool. So that's the color. Well, let's look at these other numbers. So when I'm making my sphere, I say it's 0.5, 10, 10. And you can actually see right here, these arguments are supposed to be the radius, the slices, and the stacks. So let's try to modify these, right? If I change from 0.5 to 2.5, what do you think is going to happen to my sphere if that first argument is the radius? Yeah, it'll be bigger, right? So let's give it a try. Let's look. It should be 5 times bigger, right? There you go. 5 times bigger. Now it's intersecting my donut, right? You could make it smaller if you want. Instead of 0.5, you could do 0.1, you know, and then it'll be smaller. Okay, what about the 10 and 10, slices and stacks? What do you think that means? See, now it's a little baby. You could zoom in though. You can see it's still in there. Right. Yeah, the density of segments. So if instead of 10 and 10, let's do 100 and 100. Let me put this back to 0.5. So if I do 100 stacks and 100 slices, that's the number of wires in my wireframe depiction. And check this out. If I look in here now, there's a lot more lines of latitude and longitude than there was previously, right? Now there's 100 lines of latitude and 100 lines of longitude instead of what we had before, which was 10 and 10. I could do the same thing on my torus, right? So here on my torus, I have the inner radius, the outer radius, sides, and rings, okay? So let's make my inner radius, let's do this. Let's make my outer radius a little bit bigger. I'll leave my inner radius the same. And let's do more slices and more rings, 100 and 100. So the outside of my torus will be a little bit bigger. We've not yet investigated a way to change the center, right? So now my torus is a little bigger. You can see there's a lot more rings, sort of donut longitude and donut latitude, I'll put it that way, a lot more of those lines, right? But you can't change the center, right? The center always stays in the same place. You're only rotating for now. We're going to change that later on with a bit more fancy stuff. These functions are built into OpenGL. I had to figure out how to use them, but I did not write them myself. Yeah. Okay, so that's the output, right? Let's switch gears for a minute and talk about the rest of the code, which you won't need to mess with, okay? So what else have we got? So we talked about draw object here, talked about key up, key down, and check keyboard. Let's talk about display, timer, reshape, and lighting. Okay, so first of all, lighting. We can change the lighting of our objects in a variety of different ways. So what I have here is that my ambient light is black, my diffuse light is yellow, my specular light is white, and those are the different kinds of light that I'm going to use. With in the front lighting, ambient and diffuse being cyan. So what I'm going to do here is down in my main function, I'm going to turn on lighting, which is going to now do the lighting function in addition to all the other things that are going on, right? And it's going to look pretty different. See, now it's lit, right? You can see the white parts and the greens are changing color, right? Similarly, you can see this a little better and in a similar way if instead of a wireframe sphere, I do a solid sphere or a solid torus. Oops. Oh, I deleted the color. That's what went wrong. Well, it doesn't. Well, yeah, I'll put it back. Oh, for heaven's sake. There we go. Okay. Now the colors I've assigned are blue and white, but the colors that are actually going to happen are all going to be determined by my lighting function rather than by setting the colors in the output. So if you want to have solid objects like we have here, right, with the light reflecting, you see how the light sort of spins around and reflects in the correct way, right? All that's happening as a result of the lighting function for a solid object, right? Or if I turn that lighting back off, so it's here in main, right? So if I turn that back off, it'll go back to the wireframe sort of setup. Right? Or I guess they're solid now. So now they're pretty hard to, you can't really see the three-dimensionality of it very well at this point, right? Okay. The other thing that I want to do is I want to turn on the depth test on and off. And let me show you why. I guess the rest of this, do I really care? The display function, I don't think you really need to know much about the rest of this. Okay, this is where the timer comes into play, the number of milliseconds. It's, you know, what the timer function does is it redisplays your picture with a timer that, you know, a pause that lasts for this long before, you know, the next time that it redisplays, right? You can write custom lighting code. Yeah, so if you want to, you know, come back up here into this lighting function and change things, then you're welcome to do that, right? So here's the lighting function. You can definitely mess around with this and see if you can, you know, make it do something fun. Definitely can go for that if you want. That's not required at all. Because what we're going to be doing is we're going to be looking at making our own shapes. Okay, so these are like pre-made shapes that OpenGL sort of hands to you for free, but you're going to have to make the first letter of your first name. So how are you going to do that, right? Well, you're going to be using quadrilaterals and possibly, if you like, triangles. Okay, so here's how this is going to happen. Let me undo this guy and redo this guy. There we go. Perfect. Okay. Why is this all? This got really goofy. This is supposed to be a cube. Did I delete some of the code on accident? No, I didn't. It's just weird. Okay, well, we'll just do this. Okay, so here's what we've got. We've got some quadrilaterals, okay? And let me show you what they look like. Okay. So we've got two quadrilaterals. We've got one that's green, and this green section has 4 vertex function calls. What do you think these vertex function calls are doing? GL vertex 3F, what do you think is the point of those? Yeah, the corners, right? It's the corners of the quadrilateral. So what I've done here, I have the X, Y, and Z coordinates for each of the corners of a square, right? So you can see this square lives at a height of 1 on the y-axis. These are the X, Y, and Z coordinates, right? Notice the y coordinate's always the same, yeah? So this square has a y coordinate of 1, and what's changing are the X and the Z coordinates, right? versus this one has y coordinates of -1, that's always the same, and still also changing in the x and z coordinates. So if I run this, there'll be a square sitting flat at y equals 1 and another square sitting flat at y equals 0. See? And the green square is on top, right? That's the one that lives at y equals 1. The orange one's on the bottom. What do you guys think? Make sense? The side length is 2 in that case. Yep, that's right. Because it goes from -1 to 1, right? -1 on x to 1 on x to -1 on z. Or no, I'm sorry, that's not right. Look at it this way. From 1 on x to -1 on x. That's the right way of looking at it. If you made the radius sphere 1, it should touch. Sphere of radius 1, it would touch. Yes, it should. So let's try that. So now the sphere should touch, just the tip of the sphere should touch onto the those squares that we made. Looks pretty good. Zoom. Yeah, that's pretty close. Oh yeah, sphere is radius 1, which means diameter 2. Yeah, but it looks looks pretty good, right? Okay, cool. So let's try another example. So that's making 2 squares. Instead, let's make some triangles. All right, cool. So here's what I've got. I'm making some triangles. I've got red, yellow, blue, and magenta. Oh, and that's it. Oh, and I want that bottom face back. I see what happened. Okay, I'm gonna uncomment all of this. Sorry, what happened there? Gonna have a couple things going on. Okay, so I'm gonna keep the bottom square. Okay, so this is a quadrilateral because I'm designating vertices inside of the quads block. Okay, so this quads, GL begin quads, all the way up to GL end, inside of here, I'm going to be drawing a single orange square. Down here, I'm going to begin drawing triangles. And here, I'm going to draw 4 of them, red, yellow, blue, and magenta, all the way down to GL end, right? So here's what I'm going to do. I'm going to run this guy. Oh, actually, let me turn off the sphere because it's going to get in the way. Nope, it's up here. Pardon me. There it is. Let me turn off the sphere for a second. Okay. So a square with 4 triangles, what do you think we're going to get? A little pyramid, right? And you can look at the bottom if you like. Right? The bottom's orange. Then we have yellow, blue, red, and magenta as the triangles, which, as you can see in the code, we got the orange bottom right here. And then for the triangles, red, yellow, magenta, and blue, right? Now these triangles, the vertices of them, you notice there are only 3 vertices for a triangle, right? Three corners. And you do have to be pretty careful to make sure that the coordinates of these things are in the right places, right? So when you're building this pyramid, you have to be thinking 3-dimensionally, right? And think, okay, well, I have a square, and where does my square live? Well, my square is at -1 on the y-axis and goes from -1 to 1 in the x and z directions. So if I was to pop over here for a second, let me show you what I mean. Okay, so I want to think about this square 3-dimensionally. Here's the X, Y, and Z axis. Here's the intersection points, -1 and 1, right? And I want a square that goes out to 1 and -1 on both the X and the Z axes. So what's that going to look like? Well, here's 1, -1, 1, and -1 here. And my square is going to come out like this to 1, up like that. And that's supposed to be parallel to the Z axis, but hopefully you get the idea. And that's supposed to go there. Oh boy. Okay. Right, so that square, which I did a horrible job at, my bad, is not at the level of the plane, but goes down, right? So this is y equals -1, right? So the center of this square, which I've totally mangled. Oh boy. Let's try that again. Okay. So got my coordinates. Okay. Here's the center of my square. Y is -1, which means I'm going to come up here parallel to the Z axis. And then I'm going to come across like this. And this crosses in the middle of my square, which then looks like this. That's better. This square lives underneath the XZ plane. Yeah? Then what happens? Then I incorporate some triangles at y equals 1, right? So here's some triangles that are going to build my pyramid, right? Can you see where the pyramid came from? Does that make sense? Yes, cool. Okay. Now, if you look at this, you can see one of the triangles has vertices. Let's see, that would be 1 on the X, -1 on the Y, -1 on the Z. This one, this corner, will be 1 on the X, -1 on the Y, 1 on the Z. And this one will be 0, 1, 0. So these three sets of coordinates should be one of the triangles, the right-facing triangle. So if I stop this video, pop back over here, let's look at the right triangle and see if those coordinates are the same. So we've got 0, 1, 0, that's at the top. 1, -1, 1, that's at the front. And 1, -1, -1, that's the one at the back. Same as the coordinates we had a second ago, right? So what are you going to do? You're going to use triangles or quadrilaterals or spheres and toruses if you want. You can use those if you'd like. Probably be easier to just do like a block shape to make a three-dimensional capital letter of the first letter of your first name, right? So if I was going to do an N, right, I would have to make some rectangular prisms, right? Maybe 3 of them, one for the first stick of the N, one for the diagonal, and another one for the right side of the letter N. So I'd make 3 rectangular prisms inside of this 3-dimensional space, making sure to get all of the vertices at the right spots. So what do you guys think? Oh, one more thing. This whole thing takes place in a window from -1 to 1. So any drawing that you make, the smallest that it can get in any dimension is -1, and the largest it can get is +1, right? And that'll make sure that it's a nice size when you run it. Because if you make it too small, then you'll have to like zoom in really far, right? And if you make it too big, then you'll have to zoom out really far to see it. So it's kind of a nice compromise to make it from -1 to 1. Keeps it squarely inside this window, right? The only other thing that I need to mention real quick, then we can go, is this depth test. You notice I turn this on. If I don't have this on and I try to run it, the whole thing breaks. Okay, so make sure you have your depth test on if it's looking funny. Let me show you the funny way that it looks if you don't have depth testing on. Now it's all messed up, right? See, it doesn't look like a pyramid anymore. You can sort of see through it, but it's all kind of busted, right? What's happening with that is that if you put some triangles behind other triangles, OpenGL needs to be able to figure out what's in front and what's behind so it knows what color to show you. And the way that it does that is with the depth test, right? So if you have some panels on top of other panels, then you definitely need to have this depth test on so it can figure out which panel is in front and show you which color you're supposed to be seeing. And so if I turn that back on, then it'll work, right? Okay, so now I think I'm done. Does anyone have any questions for me before we go? Okay, now it's fixed again. The first letter of your first name means you should make an H shape. Yep, that's right. Yeah, so for the H shape, you have some options. You could do like, just a two-dimensional panel, for the left side of the H, another two-dimensional panel in the middle, and a third two-dimensional panel on the right, and just do 3 panels, right? Or you could make, extruded 3D shapes to make an H. You can, so lots of different sort of approaches you can do there, right? No, there's not really a way to do curve shapes. So just do like a block S. Yeah. Again, with an R, I think it just like sort of a block shape would be fine. Right. So let me show you what I mean. I don't know how to make a half torus. I don't think that's available, but it might be available and I just never found it. But I never figured out how to do it. As far as what I'm saying with the block letters, so a block R would look like this. There's a block R, right? Or you can do a block S like that, right? And that's totally fine for this. Or you can make lots of vertices to make a curve. I would not recommend doing that unless you start incorporating some for loops, because you do not want to do that by hand. And the for loops that you make are going to be pretty complex as they move through 3-dimensional space. So I would not recommend doing that unless you have quite a few free hours on your hands, and then go for it. And it'll be a fun and interesting exercise, but that's going to be tough to do, I think, Lucas. Yeah, B. Yeah. So here's a block B. Right. That's fine for a block B. That's actually looks terrible, but you get the idea. Yeah, perfect. Okay. Any other questions before we go? Okay, well, I hope you guys enjoy this. I did want to start off with something just to get you thinking about 3-dimensional coordinates. And I think making this block letter will give you a good insight into that. As for the rest of it, good luck on your proofs and your web work stuff, and have a good rest of your week, guys. I'll see you on Monday. Yeah, you're welcome. Have a good one.